you may have heard that an expert is someone from out of town with a slide tray who covers a topic at a Mach 2 pace and leaves before you can ask questions. While I may never have gotten to your town with this tape, I hope you enjoy our time together. Because our time with you is limited, we can't investigate the depth of radar academics that are covered in my full-day seminar that is complemented by more than 400 slides and a 200-page book of course notes. But our objective, nonetheless, is to give you an overview of how radar works. Frankly, within an hour, you'll understand more about radar than I did in my first 10 years in aviation. A couple decades ago, and like most pilots, I wanted to understand radar. With my first corporate flying job came a radar-equipped Beech Queen Air, and no one could answer any of my questions. It was all trial and error, mythology, and hand-me-down procedures that didn't have any documented validity. Every pilot had personal techniques, but no one could explain radar to me with specifics. Frankly, I flew that aircraft as many professional pilots fly today. Just avoid anything you don't understand and avoid everything if in doubt. But that doesn't maximize our use of radar. It doesn't enable you to understand other radars and to evaluate information they give to you. Radar, whether ground-bound or in an airplane or the police car over the hill, is simply transmitted and received electromagnetic energy. It's an active device, transmitting and receiving its own energy as opposed to a camera, a passive device, which receives energy from another source, the sun. The sun is the transmitter, and reflected energy from it is received in your camera, and images are created in terms of light values. Radar is both transmitter and receiver in one unit. The energy returned is not only received, but weighed or evaluated, interpreted, and presented for viewing, much like an ongoing updated photograph. All electromagnetic energy travels at the speed of light, 186,000 miles per second, or 6 millionths of a second to travel 1 nautical mile. A millionth of a second is called a microsecond. 12 microseconds equates to a round-trip radar mile, the time to travel to and from a radar target. That kind of velocity applies to your VHF communications radio, the VORs you use to navigate your transponder, and the speed at which most ATC controllers speak. In some analogies, I'll even reference sound, like my voice, which of course travels at the speed of sound, not the speed of light. But all forms of energy have relationships, so the analogies are valid, although the speeds are vastly different. Back in 300 BC, Euclid noted that light reflects at predictable angles. 55 million years earlier, simple cave bats were already navigating and locating prey with echolocation or biosonar. No record reports that any bat ever became a thunderstorm statistic, so bats had effective airborne radar. A lot of time passed until the 1860s, and for the next 70 years, electromagnetic energy and the transmission and receipt of it was the focus of such researchers as Heinrich Hertz and allegedly his brothers Kilo and Mega, Faraday, Maxwell, Braun, and Christian Doppler. While they had the ideas, in most cases they were lacking the tubes to create the power, contain the heat, and display the information. All of the mechanics to make theory into reality came into being within 50 or 60 years. In the days leading up to the Second World War, English military tacticians asked Robert Watson Watt to create a British defense system. They even considered a death ray with the prospect of boiling the blood of an enemy who would be irradiated by a powerful beam. That wasn't practical, but English inventiveness did refine radar, and the English spearheaded studies to create the magnetron, an airborne power source that enabled us to carry in aircraft a lightweight, highly efficient, and powerful electromagnetic transmitter. The magnetron is the heart and soul of the transmitter, has a lifetime assigned to it, and is quite expensive. By the war's end, the cooperation between the British and the U.S. Navy and the radiation laboratory established at MIT all combined to create effective radar detection. Only as an aside did they realize the value in assessing weather, but thankfully they did. Long ago, someone asked me to define what airborne weather radar is and isn't. Radar is real-time weather, or we should say water information, since it's a water detector. It's our weather avoidance product in making deductive conclusions about what kind of weather has amassed and suspended radar-detectable water aloft. There is not an airborne radar designed for penetration of weather, only its avoidance. It's a crude electronic product, despite all the appearance of precision and accuracy. I'll prove that to you. It is not a crystal ball. In fact, what it cannot show you is oftentimes more important and hazardous than what it can display. I could explain radar and its functions to just about anyone based upon principles that you've understood since early life. You never get something for nothing. Everything in nature seeks equilibrium. For every action, there's an equal and opposite reaction. It's what you don't know that you should worry about. It's always darkest before it's totally black, and children should be seen and not had. I just threw those last two in to see if you were really listening. First, we'll see that all radar is a series of compromises, and the first is one of frequency. You must first define the target, the object that you want to detect. If everything was big and solid and close, this might not be a major decision. The first compromise in designing a radar is one of frequency and the accompanying wavelength with the selected target in mind. Every frequency has a wavelength, and that wavelength determines what size targets will be seen. Since our interest is weather, the size of the wavelength determines whether it will interact with water. Let's begin by thinking about frequency and its accompanying waveform. Notice the oscillating wave shown in Figure 1. When radar pulses energy, it has a beginning and an end. Therefore, we have a pulse length of energy. This is often called a pulse width, by the way, but the two are interchangeable. Weather radars typically transmit a pulse varying from 2 to 15 microseconds, which is millionths of a second. That means in lineal measurement, a pulse length or a train of energy is 2,000 to 15,000 feet long. We're not discussing anything microscopically small here. If you could color it, you could see it. More importantly right now, look at the oscillating wave of that energy and notice that we can measure it at any two equal points on the wave. This is wavelength. Mathematically, it's called lambda, which is what that funny little Greek character stands for. Low frequencies produce long wavelength, and high frequencies have short wavelengths. I'll give you measurements on those in just a moment. One characteristic of long wavelength is penetration. For instance, my voice is often described as deeper bass. And if you could see it on an oscilloscope, it would have a long waveform, particularly compared to the higher pitch voices of most women. I've lectured in classrooms and had the instructor in the adjoining classroom ask me to hold down the volume since my voice seemed to penetrate the wall and was audible in the next room. Frequently certainly relates to weather possibilities. If radar's mission is to penetrate weather with little interest in seeing it, we'd want the longest possible wavelength. For example, air traffic control wants its radar to penetrate the heaviest weather and bounce off solid objects, like airplanes. A short wavelength has the quality of definition because it can interact with smaller particles like raindrops. As we'll see in a minute, the highest possible frequency is light, and you've turned on your headlights in the fog. If your visual acuity was keen, you could see every droplet of that fog. But did you see through it? There was no penetration, was there? It was all definition. A tiny wavelength of light illuminating the tiniest droplets of fog. So we need to compromise between the needed and desirable penetration and definition to see what it is we've defined as our radar target. For storm detection, we want radar to reasonably penetrate a storm, but at the same time, we want it to interact with raindrops so we can determine the density, size, and shape of it. By the way, this interaction with water is called reflectivity, although it's more complicated than that, and you need to understand that too. In Figure 2, we've reproduced a frequency spectrum from sound to light. It's comfortable to use the qualities of sound and light to explain radar. A new radar student might hear that energy illuminates or irradiates a storm and is reflected from it, which makes him think of light. Then he'd hear its return is called an echo, which is measured in decibels, which leads one to think of sound. Most parents think they understand decibels. Our teenager and his decibels caused us to consider child abandonment, then euthanasia. In fact, radar is all of those things, both sound and light related. Decibels are just a measure of the total power available and what amount is released by the volume knob on a stereo, or the total power transmitted and what portion is received back at the radar site. Let's say that FM radio ends at about point A, and slightly above that is L-band radar. These designations, LS, CX, and K, mean absolutely nothing and in some cases overlap a bit. They were World War II security designations that continue to this day. However, we can consider L-band to have lots of Ls: long wavelength, low frequency, and land-based. Since you see, it's the frequency of choice for air route traffic control centers. L-band is extremely penetrating and it bounces off of solid objects like airplanes. Your transponder is, incidentally, an L-band transmitter that talks to ATC's L-band receiver. Slightly above L-band in Figure 2 are C and X-band radars, our airborne carried frequencies. Notice that they interact with water drops, and we call that reflectivity. That's not really what happens, but reflectivity is an industry standard expression, and we'll explain and use it. So ground-based radars operate around 1,000 to 3,000 megahertz, which produces a wavelength of about 23 centimeters to about 10 centimeters long. That's to say, those oscillating waves are between 10 inches down to 4 inches apart. We're not talking about anything small here. Airborne radar operates in the 5,000 to 10,000 megahertz ranges, and wavelengths are 5 centimeters down to 3 centimeters long. On the average, airborne radar's wavelength is about 2 inches long, and again, you could see it if it were colored and therefore visible. Last in Figure 2 is light, all definition and no penetration, as we've discussed. If you talk to a radar engineer and ask, what kind of radar should I have in my plane? He'd probably tell you something in the 10,000 megahertz range, I would think. You see, he's only thinking about the oscillator he has to build and what high-speed mechanical frequency generation it needs to have. Then you talk to a meteorologist and ask the same question, and he tells you, I would think you'd need something around 3 centimeters. They are both saying the same thing. One is concerned about mechanics, and the other cares only about the end product, the wavelength's ability to interact with water. Let's make all that more graphic in Figure 3. Look at how various frequencies penetrate precipitation from very light to cloudburst. Why do we have a bell in a harbor? Because it is very low frequency and therefore very penetrating. As we move up to AM, FM radio, and surely you need amplifiers and high-frequency receivers, but we normally consider this in the sound regime, notice that they too will penetrate the heaviest weather. You might get electrical disturbance, but water does not lessen the signal. Finally, we move to VHF and UHF. Whether it's TV or your VOR, DME, localizer, or glide slope, we see that the signal no longer flows around and over objects. It bounces off of them. It's line of sight, and that, my friends, is the threshold of radar. When it bounces off of something, when it reflects back toward a source. In the second part of Figure 3, we've exhibited the radar ranges and their interaction with water. Notice that L-band is exceptionally penetrating and does not see precip, although there might be a trickle of return from a cloudburst. We'll need to amplify this a bit later since we do have very limited weather displays in center radars, but from a slightly different principle. FAA radars are the topic of our second tape, How to Use Radar When Not Radar Equipped. Notice how C-band begins its electrical tricks with light precipitation, and X-band, higher frequency, shorter wavelength, does more tricks, giving more definition with light precipitation. In today's U.S. aviation industry, to my knowledge, only United Airlines uses C-band radar. Everyone else, general aviation corporations and airlines, use X-band radar for that enhanced definition and some range considerations. So definition is more precise viewing of lighter rain areas or smaller radar targets. If you have a police radar detector, you'll notice that it's identified as an XK radar detector. The police have moved from X-band to K-band radar for reasons I'll explain, but the conclusion is obvious. If you want to drive 100 miles an hour, do it in heavy rain. They can't penetrate it to detect and arrest you, and they won't chase you since only an idiot exceeds 90 miles an hour in heavy rain. Lastly, light has all definition and no penetration, so it would be a lousy weather inspection product. Also notice in comparing the improved definition of X-band versus C-band that you never get something for nothing. If you want that enhanced definition, that improved electrical interplay with water, you will forfeit energy to get it. To enhance definition, you give up penetration. This forfeiture, or loss of energy, is called attenuation. It's not a good or bad quality of radar. It is simply giving up energy in an electrical exchange with water. It's the inability to understand attenuation that has caused accidents, and that gives credence to my earlier statement, what you don't see can hurt you. What you don't see can be more important than what you do. I'll explain how you forfeit energy a little bit later. In Figure 4, you see that all energy and its frequency gets born in a transmitter-receiver called a TR or RT unit. Between the two functions is a switch called a duplexer, switching the two functions at an astronomically rapid rate. But it's easier to think of the entire box as a duplex, something that houses two units or families. Radar spends less than 1% of its time transmitting that pulse of energy. Look at it another way. Radars spend 99% plus of their time as listening devices. They await those long-distance returns before transmitting again, but don't think of this as a long time. The transmitter may be pulsing 200 to 600 times per second. This is known as the pulse repetition frequency, which is abbreviated PRF. Can't you imagine that the more time there is between pulses, the more listening time there is also? It can't transmit and receive simultaneously. So short-range radars have a very high PRF, maybe 1,600 pulses per second, and long-range radars may pulse at 200 times per second. In fact, newer digital radars change the PRF with various range selections. The receiver is a timing device. Remember I said electromagnetic energy travels 1 mile in 6 microseconds, or 6 millionths of a second. Therefore, a round-trip radar mile takes 12 microseconds. Since we know the speed of light, the receiver precisely determines the mileage to the target by simply taking the time in microseconds that has elapsed since the radar quit transmitting. And the received signal then is divided by 12 as a round-trip radar mile. Notice in Figure 4 that the energy travels a tunnel called a waveguide to the antenna. You only have one antenna, so it must do two jobs, transmit and receive, another duplexer. We have two kinds of antennas, the flat plate, the most modern, and the parabolic. The flat plate simply radiates energy forward from slots in the antenna. The parabolic is a reflective dish. The energy is radiated into the antenna from a feed horn, which is actually the end of the waveguide. It is focused in rebound, so to speak, and directed forward in a parallel in-phase path. The flat plate antenna is the more efficient in terms of power. Do you see all of those sloppy lobes radiating from the parabolic antenna? They are called side lobes around the main lobe, or focused energy beam we're trying to create. Side lobes have power, therefore they have stolen it from the main beam, so to speak. Notice the flat plate antenna has some side lobes too. Nothing's perfect. But because they are smaller, the flat plate antenna conserves a great deal more power. You might simply say it's easier and more efficient to radiate energy outward than to control the bounce back, the rebound from the parabolic antenna. Isn't your TV satellite dish a parabolic antenna? Sure it is. It collects energy from space and bounces it into the feed horn centered in the dish, which sends it on to your TV decoding amplifier. When it comes to antenna, they are like runways and rainbows. The bigger the better. The bigger the antenna, the more precise the beam or focus that can be created, and the more the radar beam is like a spotlight. Now, obviously, for the National Weather Service and air traffic control ground-bound missions, they can have as big an antenna as they'd like to engineer, build, and mount. But in airplanes, we're restricted to antennas from 10 inches to about 30 inches in diameter. The reason the bigger the better is shown in Figure 5 by a simple formula for the transmission of electromagnetic energy. 70 times the wavelength divided by the antenna diameter in inches equals the beam degrees of focus. So why did the Highway Patrol go from X-band to K-band radar? With the limited antenna space on top their dashboard, they acquired more focus, better evidence, by going to a shorter wavelength than by a bigger antenna. Shorter wavelength means less penetration, but the Highway Patrol's 1/4 to 1/2 mile area of interest makes distance a second priority, and few people will speed 100 miles per hour in rainfall. The various antenna sizes and uses, the wavelength for that radar, and the kind of beam that they radiate are shown in Figure 6. One minor caution here. You can't simply measure the physical cross-section of every antenna since each one has what's called the antenna effective area. So a 10-inch antenna might only have 9 inches of effective focusing despite its literal diameter. But I want you to grab a simple concept and come to understand radar. With your calculator, you'll see the math doesn't compute exactly, but close enough for our purposes. Besides, we're talking about how to use radar, not how to build one. The tighter the beam is focused, the more contained the energy will be, and the more energy we can direct to a target. The more energy we can retrieve, the more judgments we can make. Let's consider an analogy. Think about trying to see someone across the street. Would you use a patio light to do that? Probably not. A patio light gives a quick dispersal of light over a small distance to illuminate the immediate area. So you'd see only a vague outline of someone across the street, maybe. But with a spotlight, you can focus all the energy on that person, and when it reflects, you can determine gender, color of clothing, even posture. So we're gaining definition by putting more and more energy on the target. In Figure 7, we're exhibiting that every radar can be range limited by the size of its antenna and the resulting lack of focus of its beam of energy. All electromagnetic energy diffuses from the point of transmission, but you knew that. You've known that a VOR radial is 1 mile wide at 60 miles from the station. That's true of radios, radials, and radars. In fact, we can express that simply. 1 degree equals 1,000 feet of vertical and horizontal diffusion at 10 miles. So 1 degree equals 6,000 feet, or 1 nautical mile at 60 miles. Or, my friends, take any mileage, add 2 zeros, and you have the diffusion of 1 degree of radar energy, or VOR radial, expressed in feet. At 180 miles, every degree has diffused 18,000 feet, or 3 nautical miles. So it's not a beam of energy at all. It's a cone of energy that gets bigger with every mile it travels. And remember that airborne radar beams vary from 3 degrees to 10 degrees wide. Look at Figure 8. There is a distant thunderstorm at 200 miles where every 1 degree is 20,000 feet, about 3 1/4 miles tall and wide. Today's Learjets and King Airs have a 12-inch antenna which produces an 8-degree beam. Wow! That's 8 degrees times 200 miles and add 2 zeros, or 160,000 feet of beam height and width at 200 miles. You can see that no target is going to fill that cone. No target is going to be impacted by all the energy. Radar energy is being lost over the top, bottom, and around the sides of that target. If the target is not beam filling, if only part of the energy strikes the storm, then the return of some percentage is not a true reflection of the total energy package, is it? It's a percentage of only the portion of the power that actually irradiated the storm, while a lot of energy was lost over and under and around the storm. In Figure 9, we see that the receiver doesn't know that. All the receiver knows is, I sent out 100% of my energy, and I'm willing to receive, evaluate, and display targets based upon a percentage of that energy in return. So if energy gets lost, so to speak, the receiver never knows that. The receiver believes that the 20% being returned is 20% of all of the energy. In fact, it's 1/2 of the impact energy, and it would have been 1/2 of all of the energy too. So the receiver believes it's a 20% caliber storm. It's far more severe than that. So radar is range limited by virtue of the antenna size, because there is some point at which the beam is no longer effective or fillable by any anticipated weather, or more precisely water. At these greater distances, an increasingly lower percentage of the energy is returned for analysis, and more energy is lost over, under, and around the target. What is dense enough to return 50% of the impact energy in close now returns 20% of the energy at a distance, and it's the same storm. So it will be seen as understated or significantly underestimated in its intensity the more distant it is from the antenna. Let's look at Figure 10. While a receiver thinks in decibels, it's not totally inappropriate to call it percentage. A decibel is actually a logarithmic expression of a percentage. As energy penetrates a storm, it perceives light rain. As the storm gets dense, more decibels of radar energy are reflected from it. So we see a bell-shaped curve, which we interpret as low decibel levels as we initially penetrate the storm area, rising to heavy rain with many decibels within it, and then tapering off to lighter rain on the far side. So if 20% of the energy returns, typical from a rain area of about 1/1500ths of an inch per hour, the receiver calls that level 1 and would display it as green in a modern 4-color radar display. I'll discuss hazard expectations in a moment. Concurrent with that logic, 30 decibels, about what we'd get above 1/1500ths of an inch, up to 1/2 inch of rainfall per hour, is level 2 yellow. 40 decibels, more than 1/2 inch rainfall per hour, is level 3 red, and 50 decibels above 2 inches of rainfall per hour is level 4 purple. I think they picked purple for that level 4 storm because you're going to get bruised if you go in there. So you see that radar evaluates and colorizes the detectable level of water within a weather return. We've included the decibel formula if it interests you, although a percentage of power is a reasonable basic educational tool, an aid to general understanding. Please don't quote me as saying that decibels and percentages of power are the same thing. You might see an electrical engineer go into electron convulsions. Before we discuss hazard expectations, look at Figure 11. The National Weather Service tells us we have 6 demarcations of radar detectable precipitation. We use this scale to grade all precipitation returns, and especially thunderstorms, on radar. We might call something a level 3 echo, and that identity comes from this National Weather Service VIP schedule. VIP, incidentally, means Video Integrated Processing of Radar Precipitation Returns. And we'll see that all Level 3 returns are not necessarily thunderstorms. Level 3 simply means radar returns from water areas that exceed 1/2 inch per hour. I just explained 4 radar colors to you. The first 2 VIP National Weather Service gradients are accurately displayed on radar as green and yellow for levels 1 and 2. Let's look at levels 3, 4, 5, and 6. An airborne radar turns red at 1/2 inch per hour of rainfall rate and turns purple at 2 inches per hour. Therefore, red, level 3 color, encompasses both National Weather Service levels 3 and 4 grade thunderstorms, and purple at 2 inches per hour then includes both levels 5 and 6. So 4 colors are displaying all 6 storm gradients, but not with 6-color definition. And remember, with a 3-color radar, the red color indicates anything from level 3 reflectivity up to level 6. It simply means level 3 and beyond. What do these water levels really mean? From their presence, we deduce the kinds of convection that can hold those kinds of water levels aloft for radar detection. It takes a lot of lifting to support 2 inches of rainfall per hour, and only the kind of convection related to a thunderstorm can do that. And only a thunderstorm can produce 2 inches of rainfall per hour. Here's another thought that most radar users do not consider. Radar is geographic. If you refer to Figure 11, you need to know that airborne radar is calibrated to stratus rainfall rates. Why? It makes them very sensitive. But here's the point I want to make. There are a lot of stratus rainfall scenarios in Florida, for example, that can produce 1/2 inch of rainfall per hour. They are not thunderstorms. The cloud tops are level, low, and non-threatening, but on radar, they are still red. I've heard some idle classroom speculation about Florida-based pilots making some really bad radar decisions based on their Florida flying experience. It's alleged that they expected Florida rainfall when they saw radar red while flying in Kansas, or at least out of Florida. I doubt those conclusions, although it's dramatic. But while red in Florida can be harmless, red in Kansas means grab Toto and head for the cellar. Ask yourself this question. How in the world did 1/2 inch of rainfall gather in a dry state like Kansas? Millions of tons of air, usually from down south and the Gulf, delivered that air mass and water content, and it's not Florida, Andy M. How about radar yellow in Tucson, Arizona? Level 2 rainfall in a desert? So we think red in Florida, maybe. We need more information. Red in Kansas? Always a hazard in thunderstorm season, and watch for tornadoes. Yellow in Arizona? Wow. In our tape, How to Use Radar When Not Radar Equipped, I want to discuss with you the calibration differences between land-based National Weather Service and ATC radars, the familiar radar summary chart, the convective outlook, the severe weather chart, and other comparative differences between the pilot's view of radar and the industry's use of that same product. We'll try to help you organize and utilize these products into a productive whole. In addition, we want you to know and understand how to call for, demand, in precise terms, those radar services available to you through the center and newer terminal installations, and both of which have useful radar displays. Let's return to Figure 10 and discuss for a minute this hazard expectation that we've added to the schematic and which is displayed to the right. Level 1 returns have no hazard expectation, then why would we need them? Look at Level 2. The hazard is moderate, and you must know that this hazard extends across the entire diameter and around the entire circumference of the subject echo. Whatever convection, lifting, churning, and turbulent friction exist to suspend the heaviest level of water does exist throughout the entire cloud form. Therefore, a Level 2 hazard extends into the Level 1 area. So how can we see the entire diameter and circumference and overall hazard if we don't display that level 1 area, while that area by itself is non-hazardous? Notice that the threat for level 3 is severe and level 4 is extreme across the entire diameter and around the entire circumference, including the level 1 area. At one time, radar manufacturers considered displaying the entire echo as red if it had a red center, or the whole echo as purple if it had a purple magenta center. In terms of hazard, that would be statistically correct. But you never assist someone by denying them information like green and yellow shading. If a professional pilot were convectively trapped, so to speak, and had to make a penetration decision, some hints of green and yellow might make a lot of difference in what route was selected. We also need to see that level 1 green area to predict something called rain gradients. We'll show you that, but for now, let's say that a significant change of rain rate over a short distance is a hazard indicator. We need to see all possible water levels to make an informed judgment. So level 1 has no particular hazard unless it is tangent to heavier rainfall rates. Then it acquires the highest hazard of the heaviest water content of the echo. It is diagnostic and defines the entire echo's hazard area. Now, we've discussed what radar displays and hopefully have kept you enchanted with that, and we have yet to discuss this reflectivity issue and why a water droplet is a radar target. Notice in Figure 12 the priority of radar meteorology, or water targets. It's wet hail, wet rain, wet snow, and I'm being intentionally redundant. Wet, wet, wet. We said radar was a water detector, so we need to see how and why. It's from the presence of water and in what density levels that we make deductive conclusions about the kind of convection that might be present. In Figure 13, let's address the reflectivity issue. Notice to the left that we have 2 rain droplets and the appearance of radar energy reflecting off of, bouncing from, the first droplet. In the first place, it's not even a directed or directional rebound. It's headed in inefficient different directions, none especially en route to your radar receiver. If that first raindrop is reflective, how did the energy reach the second raindrop? If you put 2 mirrors back to back and shine a light into the first, it will reflect, but does any energy reach the second mirror? So you can see the term reflectivity doesn't really explain what's happening. In Figure 14, I want to explain something that in the absence of an engineering education, I'll call the belly flop principle. We've all done belly flops in swimming pools, and they hurt. They hurt because of the boundary resistance of the water's surface. But you did go in the pool thereafter. And in that same way, the impact electromagnetic energy does encounter boundary resistance, and a trickle of energy is truly reflected. But the energy continues to penetrate the droplet. Notice how the energy resisted and returned on the front side has no particular directional input. It may ricochet in a multitude of directions. But the backside of that raindrop is shaped like a parabolic antenna. Its resisted energy is actually focused back to the antenna and the receiver. To be sure, this is a trickle of energy. If airborne radar had to rely upon it, we'd never see a thing. But this will be reviewed again in our next tape because it does explain the weather capabilities of ATC center radar. In ATC's case, it's a trickle of 5 million watts of power, and that's an awesome trickle. So long wavelength radars can get a trickle of energy and a trickle of weather information that can be useful to us. While boundary resistance returns are there, they are totally insignificant to X-band airborne carried radar. And we'll learn that trickle returns give only crude and limited weather displays for center controllers. But like the old adage, it's better than nothing. And I'd certainly like to know something about it if I did not have radar or the radar on board failed. I've used it many times in the past 3 decades. S-band radar, which has 10-centimeter wavelengths, about 4 inches by the way, is used by the National Weather Service, uses both principles of dipoling, which we'll discuss in a second, and boundary resistance. One radar site that I visited in Norman, Oklahoma uses 1 million watts of power focused to a 1/2 degree beam or cone. It could detect the lightest rainfall and continue penetration right into the heart of the storm. One meteorologist claimed he could track a large bumblebee for a few miles. I presume the bee lost any interest in pollination. In Figure 15, we're showing what really happens when X-band or short wavelength radar impacts and transits water drops. They penetrate and impart a charge to the water droplet, aligning all of the droplet molecules in phase and in parallel with the impact energy. They impart energy. Did you understand that? That droplet becomes charged, and because everything in nature seeks equilibrium, a charged water drop does not want to be charged, so it begins to discharge. It transmits. We are creating meteorological transmitters that we want to locate and analyze. This is called dipoling, 2 poles, di, which is the electromagnetic tap dance that occurs within that water drop during the charging process and by which it becomes a transmitter. The omnidirectional discharge of energy is called the scattering of radar energy, and what is directed back to you is called backscatter. If it's not wet, it does not have the molecular versatility to dance, to align themselves and transmit or scatter the energy. Also notice on the right of Figure 15 that about 3 or 4 or 5 vectors of backscatter are directed back to the receiver. That's right, about 5 or 6 or less of a 360-degree circle of the raindrop's radiated energy is actually returned to the receiver. In radar's early days, we had to boost the transmitted energy up to 60,000 watts of power to equally boost that backscatter of energy up to a detectable level. Today's radars use power levels from 20 watts to 125 watts to 1,500 watts. Those modern digital receivers can take a token signal, amplify it, interpret it, and display a superb picture. If 20 watts of power seems insignificant, and I did hear one radar educator say my personal standard is 5,000 watts of power, let's consider that the space probe Voyager has been transmitting pictures from 1 billion miles in space with 3 watts of power. You can imagine it used the lowest, most penetrating wavelength possible, and the size of the receiving antenna must be awesome to intercept that massively dispersed signal. But if 3 watts of power can deliver pictures from 1 billion miles away, 125 or 1,400 watts of power should meet your needs for the next 100 miles or so. So let's return to Figure 12 and talk about these meteorological priority targets. You see, a wet hailstone has 2 kinds of radar return. Its hailstone is a solid, usually smooth because it's wet, and it's surrounded by a dipoling water jacket. It's potentially a double return, depending on the size of the hailstone. That's a superb radar target. Next is the raindrop. That's the target for which airborne weather radar has been engineered. Its versatile molecules can dance readily. It becomes a fine transmitter with the properly selected wavelength. Rain droplets are ideal targets with diameters of about 1/10 to 2/10, the size of the wavelength. Next, and now losing good definition, is wet snow. It's becoming crystalline. The molecules aren't free to align and dance, and it becomes a weaker radar target. In that same vein, look at dry hail and dry snow. No free-moving molecules. Energy ricochets or bounces off of in undirected paths, and they are poor radar targets. Let's look at Figure 16. What will radar not detect? Well, it will not see fog, cirrus clouds, and small dry snow and hail. In other words, it will not see or detect things crystalline or significantly smaller than the wavelength itself. If it won't paint cirrus clouds, hail, snow, or crystalline targets, how effective is airborne radar in measuring the height of an altocumulus cloud or thunderstorm? You might assume that you've reached the top when you run out of water, and you will underestimate the actual top by 10,000 to 12,000 feet. And turbulence will extend above the actual top by another 10,000 feet. It's an interesting math exercise, but airborne radar is a lousy product to determine the tops of thunderstorms, and land-based radar has its liabilities too. In fact, look at Figure 17, where we've depicted a ground-based radar attempting to detect the cloud top. Remember that beam dispersal? At some point, as the beam is elevated, it will break free of the cloud top, and it is no longer beam filling. Energy's being lost. In addition, the tops of the clouds are not radar detectable. So when you see radar charts and storm tops, you think they are at least that tall, and probably 10,000 feet more. Can you look at a cloud and determine its potential as a radar target? Absolutely not. Over the years, even your professional pilot pals have made maintenance write-ups about radar, quote, did not paint an obvious thunderstorm, unquote. Unless you had two radars side by side and one did paint it, you can't make precise judgments without knowing the water level, droplet sizes, and such in the suspected cloud area. In fact, one of the best write-ups was by a first officer who was obviously distracted. He wrote, "The radar doesn't." Yep, that's it, doesn't. The A&P mechanic signed it off, as it does now. We have discussed that 4 levels of color are presented on the scope, tube, display, whatever you like to call it. The correct name is PPI, Plan Position Indicator. You've seen that in your National Weather Service radar reports. PPINE, PPINE, Plan Position Indicator, no echoes. Oh, good news indeed. Or PPIOM, out for maintenance. Or PPINA, not available. As we show in Figure 18, it's a plan view, like looking down on the plans for your house, and it's positioned to the nose of the aircraft. It's like a slice taken out of the storm or a slice out of a loaf of bread. And in theory, you can take slices out of that storm at various levels to inspect them. That slice concept is pure theory. We saw how the cone diffused. More practically, you're getting an average water content in a tall and wide scan of the storm. You see range selections on the display. How about that 300-mile range with a 10-inch antenna, 10-degree beam, as in a Learjet? Remember what we said about diffusion? At 300 miles, every degree is diffused 30,000 feet, and you have 10 of them. A 300,000-foot beam vertically and horizontally. What thunderstorm out there is going to fill it? None. If you even got back 20 decibels or green from 300 miles, you'd have a remarkable display. In fact, in the early days of ineffective radar, that was an axiom. If you get any return, regardless of density, from over 75 miles, plan a deviation around it. We've extended that distance now with some digital magic, but at some point everything will be understated by virtue of the inability to fill the beam and receive any adequate amount of radiation. You are, in fact, range limited somewhere around the 80,000 foot point of the beam. With a 10-inch antenna and its 10-degree beam, that's at about 80 miles or slightly over that. With an airline antenna, 30 inches or 3-degree beam, that's at about 250 miles. I'll repeat, you are range limited by the size of that antenna. So you see that radar, with its limitations in its display, is not the panacea to all of your weather problems. I told you it was a crude electronic product. It has geographic interpretation problems, range problems, target considerations, and some experience is required in interpreting the display specifics itself. In Figure 19, we're showing another limitation in radar displays. Here's 2 PPIs, one in a 30-mile range and the other in a 200-mile range. Obviously, the size of the display did not change. What did change is the value, the distance, represented by the pixels of light on the screen. Whereas one dot of light might represent distances in feet at short ranges, it might represent miles at vast ranges. When meteorologists discuss unique storm shapes like hooks, pilots need to know that airborne radar can only see these things at short ranges. You don't see a unique shape with big range selections. And in fact, the red area might not even be sizable enough to light 1 pixel at a distant range selection. The storm will appear to grow and intensify as it approaches the aircraft, with shorter or smaller ranges selected as distance permits and with better pixel display. One of the true skills of radar use is called tilt control, and we're showing that briefly in Figure 20. Obviously, to get water returns, the radar energy must be directed in the vicinity of water. Good water returns are located up to and just above 25,000 feet MSL. Most seminars will concentrate on tilt management and tilt techniques to eliminate heavy decibel ground returns from too much down tilt, and to not tilt so high that the energy is invested in crystalline cirrus clouds of no radar value. That 25,000-foot level is the diagnostic level used by the National Weather Service for determining the nature of severe storms. Flying below 25,000 feet, we'd expect to direct the energy upward. Much above 25,000 feet, a radar user would be using down tilt. Radars allow tilt management of typically plus or minus 15 degrees. Therefore, the cone of energy is controlled by the pilot to examine the size and density and shapes of convective rain areas. Speaking of shapes, Figure 21 identifies the classic shapes that most pilots mention and avoid: hooks, fingers, scallops, steep rain gradients, and rapidly changing echoes. A hook is a legendary tornado indicator, usually appearing on the south or southwest side of the storm, being fed by southerly flow from typically the Gulf. Fingers and scallops are hail clues. Steep rain gradients and rapid changes in an echo indicate rapidly and violently changing conditions. I've always simplified echo interpretation by a simple conclusion. We have two kinds of thunderstorms, the general or air mass type and the severe. The key word to either is symmetry. The typical summer thunderstorm grows symmetrically, gets very red symmetrically, and dies symmetrically within an hour. When it gets asymmetrical, this is caused by violent up and down drafts or by movement towards water, distortion by rotation within it, or hail carrying water out of the storm that creates these unique shapes. So pilots avoid echoes that take on unique shapes, change rapidly, or show steep rain gradients that deviate from symmetry. And remember, the shorter the range selected, the better radar display we get with short distance pixels of light. Unlike general aviation operations, most airlines have their own thunderstorm avoidance criteria, so here's a simple one for you. Avoid convective level 3 red returns by 10 miles below 20,000 feet and by 20 miles above 20,000 feet. Avoid the downwind side of red echoes where the hail and turbulence can be ejected by the storm. Be very wary of the south and southwest corners of violent storms and the south area of a line of thunderstorms. A thunderstorm is a heat machine and its fuel is water. Especially in the Midwest, the source of that water is the Gulf, which is typically south and southwest of the echo. Rotating inputs to the storm can give birth to tornadoes. Avoid overhangs. They might be the water accompanying hail as it's ejected from the storm, usually on the downwind side. Lastly, we need to mention attenuation. Attenuation, by definition, is the lessening of or the loss of energy. A choir director might attenuate, silence, or command less volume. from the base section, so to attenuate is simply to silence or lose power. Radar energy is converted to heat by the interaction with oxygen and water. Since the amount of oxygen in the atmosphere is a constant, the more water we encounter, the more the heat conversion takes place. As a matter of fact, your microwave oven is an attenuation oven. If you look in the back, the power source is a magnetron. Incidentally, water attenuation is a function of wavelength. The shorter the wavelength, the more electrical interplay there will be with smaller water drops, and the more available water drops there are to absorb energy. To attenuate means concurrently radar's inability to continue penetrating a water area. It's the point at which your radar beam is energy deficient. The hazard of attenuation is that returns may appear vastly understated. A dense water area might appear to be a narrower, thereby inviting band of weather that might be easily transited. With an energy loss, the axiom is simple. What you don't see can be far more hazardous than what you do. In our tape's beginning, I said, you never get something for nothing. Let's return to Figure 3. Look at the difference between S-band radar's definition and penetration as opposed to X-band. To gain definition, the ability to see and display lighter rainfall areas, you first must have a wavelength that will interact with small water drops, and you must impart energy to those water drops. To impart energy, you give up energy. To deplete your energy is similar to beam spreading and the inability to fill the beam. Remember that the receiver knows what the transmitter sent out, and it weighs that against what comes back. What's being sent out and is interacting with moderate to heavy rainfall areas is diminishing rapidly. Therefore, only understated returns can be received. In thunderstorm displays, that attenuation curse is always on our minds. We suspect attenuation anytime we are in moderate to heavy rainfall. Remember, radar is an avoidance device, not one of penetration. We are suspicious of what lies ahead and usually think it might be more severe than displayed. With ice on the radome, the antenna housing, we suspect that energy is being dispersed by the ice and not focused as engineered. However, the attenuation red flag is rather classic and simple. It is, as shown in Figure 22, a bowed-out or concave backside, a steep rain gradient on the backside, and let's discuss the inability to paint the ground beyond the subject echoes. Notice it's all backside, more distant symptoms. That's your inability to penetrate, and that's easily explained. Look at Figure 23. Assuming we have the circular bullseye thunderstorm shown on the left, remember the bell-shaped curve in Figure 10. We had a rising level of decibel returns the deeper we penetrated the storm area. That means more interaction with water drops and more energy invested in those water droplets. We are forfeiting energy throughout the entire exercise. Finally, the energy just depletes, peters out, or diminishes rapidly in the heaviest rain area. The receiver, in turn, hears exactly that. Light rain, green returns, increasing to moderate yellow and on to red, heavy rain. Then the receiver hears the energy fall off rapidly. A steep cliff or energy loss which the receiver believes is valid, or the receiver believes, because it has no reason to believe otherwise, that the energy has exited the backside of the storm and that a very steep rain gradient exists there. No, no, no. It is a pictorial representation of rapid energy depletion. A steep rain gradient on the backside of a storm is a red flag for pilots. Look at Figure 24. On the left is a National Weather Service display of a huge storm area in the Deep South that occurred in 1977. A competent captain in an airline DC-9 attempted to penetrate that storm with fatal results. Why would a heavily respected airline captain make such a tragic error? Look at the right side of this comparison. It shows all of the symptoms of attenuation, bowed out and concave backside and steep ring gradient on the backside. In addition, and listen now, this is very important, had he tilted the beam down and attempted to reflect energy off the ground behind the storm, he'd have found he couldn't do it. Ground is highly reflective, so if there isn't enough energy left in the radar beam to penetrate the weather and bounce back from the ground behind the weather, your radar beam is being attenuated. So the defensive radar rule is simply this: if you can't ground paint through it, don't you dare fly through it. In that captain's defense, let me add that radar training was exceptionally poor in 1977. He was denied information from his company, the Center, and the National Weather Service, information to which he was entitled. Many procedural changes came about because a fine man, Captain Bill McKenzie, was isolated to the use of the crude electronic product on board his airplane in lieu of the information he needed to make safe and conservative decisions. Captain McKenzie deserves defense beyond some self-serving and critical analysis of his sad accident. In another tape, I'll explain to you that despite that sacrifice, those changes that were mandated were not in place some 9 years later, and 7 more people were lost to eternity. Had he tried to paint the ground behind the Echo, he could not have done so. If you can't paint the ground through the weather, don't you dare never ever fly through it. Lastly, in Figure 26, we're reprinting a schematic courtesy of the Honeywell Corporation about the safe area for people around an airplane that's transmitting radar energy. Air traffic controllers ask me this a lot: are we exposed to all the energy of all the inbound airplanes? Well, the glass in the tower deflects most of it, and radar energy is not accumulative. 4 things hurt people when exposed to radar transmissions. Radar energy is power, which is heat; frequency, which is wavelength and therefore penetration. Then there's the antenna size, which can concentrate the heat and the penetration, and of course time. How long did you microwave or barbecue that unsuspecting soul? But notice that even with those 4 considerations, the typical corporate power radar has safe distances at 10 to 15 feet. And that's with a 1400-watt radar. To be sure, we never want to irradiate anyone needlessly, and you need to consider the effect of radar energy on someone with a heart pacemaker. However, you can see that minimum distances relate to the low-power radars we use today. In the old days, with 60,000 watts of power, we could create sparks in steel wool at 75 yards. One engineer told me that with a 100-watt radar, you could put your tummy to the radome, and there was neither the penetration or the power to burn tissue. No one would be simplistic enough to put that in print, but it's probably true, and we need to find and experiment with that engineer. Let me reiterate, I cannot cover all the facets of radar with you, those that I would cover in an 8-hour seminar, as I've done for universities, major corporations, airlines, and the military. But I trust that this overview has expanded your understanding, enhanced your aeronautical education, and most of all, Scott and I hope it's entertained you.